All right, so we left off last time around here, angle of twist. And again, this is only valid in the elastic range, right? Because the the stiffness, right, the modulus here is calculated in the elastic range, right? This is where it comes from. It comes from doing shear modulus in the elastic range. So let's see, torsional loading changes along the length. Right. Oh yeah, this is just saying if you have, the longer this is, right, remember the angle of twist depends on length. So if you do have a length of a shaft that has different cross sections, and you want to know, and also different different torques going on, right? You can find the angle of rotation as the sum of all segment rotations, right? So for example, you know, you're looking at one end as, say you're taking from the B end, right? You take this this length and this diameter and you get an angle of twist, and then you add in this length and this diameter, and then now you've got another torque here, right? So you've got a new sum of the torques at this point, and you just take it piece by piece. So that looks kind of like, oh, doesn't look like this. Yeah, well, we'll see it in the example. So here's an example. This is not varying in diameter, but it is variable length that we're looking at here. If you were to look at this shaft, right, this shaft is fixed at both ends, right? It's embedded in wall A and B. We're saying it's embedded. I have no idea what's going on. But we want to find the torque reactions at A. So maybe there's something in the middle causing some torque on this pipe, and it's embedded in both ends. So there's a resulting torque, right? So the free body analysis tells you, oh, TA plus TB is 90 pound-foot, right? And we know it's, well, I mean, this one is kind of obvious that it's going to be, I mean, it's split in half, but this is hollow and this is solid. So if this was a solid beam, it would be obvious, right? It's split 50-50, but it's not. This half is hollow and this half is solid. So this is not enough to find the torques at the end, right? So you'd have two components and the deformation must be the same, right? So the overall angle of twist needs to be the same. So here you could actually use that to help you solve your problem. And you can see here the phi, right, is going to be phi1 plus phi2. And phi1 comes from the tension, or sorry, the torque on A, right, times the length. And J1 is the modular, the polar modulus of, you know, this first section, and G is obviously the stiffness of the material. And then you've got torque B times its length, right? Now, if the lengths are both the same, which in this case they are, right? And notice these are negative values, right? We're saying at this intersection of this, the overall phi is phi1 plus phi2. However, we're saying this equals 0, right? Because overall, at one end, there's no deformation, there's no twist. It's in the middle that it's twisting. So phi1 equals the negative phi2, right? Or equals phi2, sorry. Because in the center is where the full deformation is. But this is made up of basically the solid portion and the hollow portion. Whatever twist the solid portion undergoes, the hollow portion undergoes, right? Because they're meeting in the middle. That's where the load is. The overall twist is in the center. So you can rearrange this and just solve for one tension with respect to the other one as a function of the different lengths. Notice the material is the same. the polar moduli are different, right? So now you've got the lengths, the different lengths, which in this case are the same, right? So in this case of the identical lengths, these cancel out. So now you've got the polar modulus of section 2, which is the hollow one, over the polar modulus of the solid portion, right? And that gives you the tension in B with respect to A. So now you've got two equations, two unknowns, and now you can solve for you know, each of the tensions. Oh, here's the original equilibrium equation, right? You can get this in terms of T sub A. Now, again, you're not given any information about the, well, let's see. Yeah, you don't have enough dimensional information to figure out what the J's are. So polar modulus of elasticity, or polar modulus, you just need to know the diameter for the solid. For the hollow one, you have to know the OD and the ID. Let's see, problem 3.4. Oh, wait, this is the problem. Oh, I messed up the order here. Let's see. Yeah, we're going to do this on the document camera. So I don't know why. I must have moved the slide accidentally when I was fumbling with PowerPoint earlier. All right. So we're going to take these concepts and we're going to look at this assembly. So two solid steel shafts are connected by gears. So here are our shafts. It looks like they're made of the same materials with the same G, the same stiffness, right? Shear stiffness. 11.2 times 10 to the 6th PSI. And the allowable shearing stress is 8 KSI. Determine the largest torque, T naught, that may be applied to the end of shaft AB. And part B, the corresponding angle through which the end A of shaft AB rotates. So that's a little confusing to follow that part B. Part A is fairly straightforward from the concept of thinking about it. All right, I know that the maximum shear stress allowable is 8 KSI. What's the largest torque here? So I need to find what the shear stress is. I need to be able to relate the torque here to the shear stress in either one of these shafts. And for part B, the corresponding angle through which the end A of shaft AB rotates. If you look at the way this setup is, we have something over here. We're assuming this is fixed over here, right? So this torque is going to twist the greatest, right, over here. Now, obviously, the torque's going to be transmitted through this bar, but this is acting to resist the torque, right? Everything else is acting to resist the torque. So really, the largest, the angle of twist we're interested in is over here on the point A. All right, so let's look at statics. We're going to go back to statics. And this is why statics is a prerequisite for this course and dynamics. You got to know how to do free body diagrams. You got to know how to set them up. You got to know how forces transmit along things. And we're going to find a relationship between the torque in CD and the torque here at, applied torque T naught. We'll do the kinematic analysis on the gears. So we're going to relate here the angular rotations. Again, something we'll do more of in dynamics. And then we're going to find the allowable torque on the shaft. And we're going to choose the smallest. Torque for that. Corresponding angle of twist, right? Angle of twist for each shaft, and then the net angular rotation of end A. So let's look at this on the page here. This will take up, I'm sure it'll take up 2 sheets. Well, it did in my notes. So if it took up 2 sheets of my notes, it's going to take up 2 sheets here. All right, so the first thing I'm going to do is I'm going to draw a free body diagram of these gears. And I'm going to draw it from like you're looking head on to the gears. So let's look at that free body diagram. And I'm going to, let's see, I'm going to separate them by a slight distance just so I have room to put notations in. So the gears are actually coupled with each other, right? And but I'm separating them just so I can see what's going on a little bit. And they'll be coupled with forces. So this is C, and this is B. So again, this is looking head on, right, from the front. I'm going to call this torque T, well, this is T naught, obviously, but this is the torque AB, which equals T naught, right? That's the torque that's being applied at A. We want to translate this somehow to what's going on over here. We've got a force and a force. And let me go through why I'm drawing them like this, right? Gear C is resisting movement, right? Well, maybe I should start from gear A. You turn this gear, right? And the gear is rotating in this direction, clockwise. As it acts up on gear C, there's a force, a resistant force against it, right? This is the reaction force. This force here is the reaction force of C on B. Analogously, this force here is the reaction force of A on C, right? This is the coupling force between them. It's equal and opposite. Let's see. What else do I need? Do I need those forces? No, I guess I don't. These are, I'll just call these the gears. From the front. All right, so let's look at gear B. For gear B, oh, you know what? I need to draw a little center point here. The sum of the moments, I'm going to just call the center point, I'm going to use the letter as the center point, right? So C and B. The sum of the moments about B is equal to 0. And you can write this as a force times a perpendicular distance. So we've got a force. Oh, that's what I forgot, a distance. Well, yeah. The radius here, these are so tiny. This is 0.875 inches. And this one over here is, oh, that's a radius, 2.45 inches. For a minute there, this arrow seemed like it was coming out of the page. 2.45 inches. I'm just getting old and blind. All right, so gear B, the sum of the moments. So what does that mean? Well, the force here and the torque are both moments, generating moments about B. The torque is going counterclockwise, right? And I mean, the torque is a moment. So we've got a negative T naught. And let me just make a little, right? Some of the moments is counterclockwise, is positive. And I've got a force, F, that generates a counterclockwise moment. And that distance is 0.8 0.875 inches from the center of the gear. So this is for gear B. For gear C, again, the sum of the moments of C is equal to 0. So what do I have here? Oh, I need to draw the other torque. I've got a force acting on C. I've also got a torque. Let's call this torque CD. I knew I was forgetting something, right? So as this gear applies a torque, it's applying a torque to this gear as well. And again, notice the directions of the torques and the forces. You've got a negative TCD, right, plus F times 2.45 inches, right? All this is a force times a distance. And these forces are equal and opposite. These are equal and opposite, right? So we can basically solve for one in terms of the other. So for example, combining these two, we got TCD equals T naught with a ratio 2.45 over 0.875. Right, they're both equal to 0. They're both equal to each other. And you can rearrange this thing, cancel out the forces. Let's see what else. Or I mean, you could do this by division, right? You can just divide them. And we've got an equation here for TCD in terms of T naught. Right? So that's just algebra between there. So now we have the torque, let's see, the largest torque. We have the torque of CD with respect to T naught. Now notice here, the torque in CD is 2.8 times that of T naught. So the question comes up as well, is the limiting shear stress going to be actually occurring in this rod, right? So we got to figure that out. So that's the reason to try to relate these two. Now, the other thing we got to do is we got to do a kinetic a diagram here. And what we're doing that for is to get a relationship between the phis. So I'm going to draw these out again, these two gears. This time I'm going to draw them in contact with each other. This is RB, and this is RC. And remember, these are 2.45 inches and 0.875 inches. What I want to do here is I want to draw in an angle. So the maximum angle of rotation on C is going to be out here, right? It's the furthest from the fixed point. So it's going to depend on this length. So this phi here, phi C, that's fishy. So you've also got a rotation at B, right? And these two are coupled, right? You can't rotate one without the other. So we can write an equation that shows the radius of B times the angle phi B equals RC times phi c, right? This is basically just it's angular, it's just simple angular mechanics, right? It's the radius times the angle gives you that perimeter, right? Because remember, one is a smaller radius than the other. Now, if they were the same radius, we would just say phi c equals phi b, but that's not the case, right? It's a ratio between them. So from here, you can find the relationship between phi b and phi c, RB, right? So we have another relationship, and this turns out to be just, if you plug in the radii, 2.8 BC, right? So this means that for every, this is kind of opposite, right? For every degree or radian, this is technically in radians, every radian phi c rotates, right? Phi b will rotate 2.8 times that. Or phi b has to rotate 2.8 times that of phi c to make it rotate one time, right? That's all it's saying. That's the ratio, the gear ratio. All right, so now that we have these relationships, we're actually ready to start solving the problem. So for part A, we're interested in the torque. So the largest torque, T naught max for shaft AB. And the tau allowable is 8,000 psi. That's our maximum shear stress, right? And that was given to us up in the problem statement. I'm just going to get a cough drop here. All right, so then let's see. Oh, yeah. So now we just use our shear stress equation, right? So the shear stress is the torque times the radius divided by the polar moment of inertia, right? And we know what our allowable shear stress is, so we're going to rearrange this solve for torque. So torque, let me draw an arrow. Torque is equal to the polar moment of inertia times the shear stress divided by C. In this case, we're looking at the shear stress in the rod itself, right? So C is the radius of the rod. So let's write this out. It's going to be, I'm going to put the shear stress first. I'll have 8,000 psi. For my polar moment of inertia, these are solid steel shafts. So that's based on the radius of the shaft squared, or to the fourth. So it's pi over 2. The radius of these, I'm just going to write it in here. Right, half of the diameters. Be careful when you're given radii and diameters. What did I say? 0.375 inches to the fourth divided by C again is 0.375 inches. And here you've got this pounds per square inch. So you lose you lose the inches on the bottom. Wind up with pounds times inches to the second divided by inches. So you wind up here with a torque of 662.7 pound-inch. This is the torque in AB, which is equal to the torque T naught, right? That's 662.7 pound-inch. Now, this is the limiting torque for AB, right? We need to find out, well, what about CD, right? This is based on the shear stress in that 0.375-inch rod. Now we say for shaft CD, TCD equals 2.8 times T naught, right? So that's, also let me make a note here, and C equals 0.5 inch, and your allowable shear is still 8,000 PSI. We'll keep that in mind, even though it's right above us. So now what I'm going to do is I'm going to check I can work either direction, right? I can check what the shear is with that torque. Well, let's just set this up, right? So TCD is equal to 2.8 T naught, right? Which is also equal to, so forgetting this, right? We know that the torque is the polar moment of inertia. I should put a subscript on that. Well, times the shear stress divided by the radius. So now I'm looking at this in the context of rod CD. So I'm going to write this, I'll just write allowable shear stress, J, C. I think I'll call this CD, so you know. Up here, you can go in and rewrite it in if you want, AB. So I'm going to put those numbers in. I need to bring the 2.8 over. So I'm going to make this an arrow. So the torque is going to be, we're going to have the allowable shear stress again, 8,000 PSI. Now my J, this is also still a hollow shaft, or sorry, a solid shaft, pi over 2, 0.5 inches to the fourth. And then I'm dividing by 2.8, so I've got that over here now. And then C is 0.5 inches. Right, so just rearranging this. And this gives me T naught equals 561 point, oh, it looks like I didn't carry any more decimals. 561 pound-inch. This is based on not exceeding tau allowable equals 8,000 PSI in CD, right? So that's the max permissible torque, max permissible is the smaller value. Why is that? Right? Because T naught, and you kind of could have seen it right here that CD was going to be the limiting case, because we're going to wind up with a larger torque. I mean, you had to still do the calculations, but TCD is 2 times that of T naught. And just based on the diameters of the radii in this case, you find out that the torque in this scenario is 561 pound-inch. Up here for AB, you can go all the way up to 662 pound-inch and never exceed, well, not exceed the 8,000 PSI allowable shear stress in shaft AB. However, if you go to 662 pound-inch of torque, it's going to be a higher shear stress than 8,000 PSI in CD, right? Because it's 2.8 times that, right? So you could actually solve this. It's 2.8 times the torque. You could solve for the shear stress and see what that's going to be. So that's the other way you could have approached this problem, right? You could have plugged in the torque. Well, it would have been more complicated because you wouldn't have got an answer right away. You could have plugged in this value here, right? Calculated what your shear stress was, forget allowable, just calculate the shear stress and realize, oh, my shear stress is greater than 8,000 PSI. Now I have to go back and solve for torque based on a limit of 8,000 PSI. So this was the shorter way to do it because you're testing each one. You're saying, okay, what torque do I need to get in AB to get my max shear stress? What torque do I need what torque do I need to apply to get in CD to get my shear stress of 8,000 PSI? And you can see the torque is lower. So this is why it was important to relate those two way up here, right? Relate the two torques so you could solve between them. All right, so now the next step is part B, is the corresponding angle through which end A of shaft AB rotates. So let's just let's start on a new page. Sample problem. Sample 1.5. Sample problem 3.4. Chapter 3. All right. Part B. To find the, what do we need? The angle of rotation, corresponding angle through which end of A. Now the angle of rotation at end A, find angle of twist for each shaft. So you're going to apply a torque. And that torque is the torque is going to be transmitted through both of these shafts. And this is stationary. So this shaft is going to twist, right? And this shaft is going to twist a certain amount. And one of these is limiting it. It's not clear what, right? So let's look at each shaft. So shaft A, B. Remember, the torque AB is just equal to the torque T naught, right? So we're going to use the limiting torque, the corresponding angle through, yeah, so that was not clear from the problem. What's the largest torque that may be applied? And then the corresponding angle. So corresponding to that largest torque. And so we're going to use the 561 pound-inch. Oh, I know why I put the period before. It's because the LB looks like a 1 to 6. So I'm trying to separate the the symbol pound-inch. So this is the limiting torque from part A. And let's look at the angle of twist, phi AB. What does it say? Corresponding angle through which end of A. Yeah. So phi AB is going to be the torque AB times the length divided by the polar. Let's put the polar moment. The stiffness is the same. All these subscripts. So AB has its own torque, length, and polar moment of inertia. The stiffness for each one is the same, 11.2 times 10 to the 6th. So what are we doing here? We're going to find the angle of this. It's 561. 24 inches. Polar moment is going to be, unfortunately, I didn't actually calculate a number before, so let me just write it in. 0.375 inch to the 4th. And then we've got 11.2 times 10 to the 6th psi. This gives us 0.0387 radians. Now, we're not done here. Remember to multiply, because we've got to check something else by 180 over pi, 4 degrees. So phi AB becomes 2.217 degrees. So I'm going to carry that number through for a bit. Let's look at shaft CD. So remember, this is the angle of twist only for AB based on its torque, right? It doesn't include the effect of CD. So now we have this same torque is on CD, and that's going to cause an angular rotation as well. So let's look at that one. This is also the torque CD. This is the length CD, and this is J, CD, and G. Just remember, this is 2.8 T naught. I mean, I could have just written it here. I don't know why. So for up here, we've got 2.8 times the 561. What time is it? Oh, pound-inch. And then we've got a length of 36 inches. And then the polar moment of inertia for that shaft, pi over 2 times 0.5 inches to the 4th. And then 11.2, G is 11.2 times 10 to the 6th psi for the stiffness. And this turns out to be what? Let's see. 0.0514 radians. So phi CD is 2.947 degrees. Now, gears B and C are related remember we calculated up here the relationship between the angle of twist phi B equals 2.8 DC. So phi B is equal to 2.8 times 2. I'm going to round here to 2.95 degrees. And this gives us 8.26 degrees. This is a 2.8. All right. So what we're seeing here is the end of shaft A can twist 8.26 degrees plus the twist in shaft A, well, AB. So phi A equals BB plus phi AB. And that equals 10.48 degrees. This is a little confusing. So I'm going to walk through this addition again, right? Let's see something here. All right. The first thing we did is we said, okay, we have this system that at some point, I mean, look at this system, physically what's happening. You're applying a torque here, and it's a maximum torque, 561 pound-inch. Once that torque's applied, everything's going to deform a certain amount depending on the properties of the material. Because of that deformation, let's pretend there's no deformation at first in AB, right? The shaft AB, let's think about the way this is working, right? You start turning this, and you work backwards from the fixed point. This shaft starts twisting. And based on this torque, you can twist this shaft only so much, right? This gear is coupled to this section here. So you're going to get a certain angle of twist corresponding to that. And that's going to translate into a certain angle of twist over here. Remember, your torque here now, this is if the shaft didn't bend, right? If the shaft didn't bend, you would turn this, like you would be able to turn this limited based on this angle of twist, which gets magnified, right? The angle of twist gets magnified because of this relationship. So whatever angle of twist this gives you, what do we get? 2 point, where the hell is it? Oh, it's down here. You know, we got 2.95 angle of twist in CD. You're getting 8.26 degrees of twist or of rotation, I guess, in this gear. And that's with AB not twisting at all. So this torque, remember, also torques AB, right? And that's going to torque, or that's going to twist a certain angle as well. And so that's why we're adding in the 2.217 up here, which appears I rounded up to 2.22. To get the 10.48. Other questions about this one? This, again, this is one of those classes where the math is really not that hard, right? The equations are not that complicated. How to use those equations, this is why I never have problems with open book tests in engineering, because it doesn't matter, right? I'll give you an equation sheet, or you'll open your book. You need to understand physically what's going on, how these forces are transmitting, what stresses they're generating, or in this case, what's the angle of twist they're generating, and how these things add together. So that's example 1.5. This is actually sample problem 3.4, I believe. Oh, wait. I don't know. I got to check something's wrong here because example 1.5 and sample problem 3.4. Maybe it's 3.4 in the PowerPoint. That's why. All right. I don't really have much more time to get into this next example, but we'll do this next time. These are the slides on this particular problem. So, I mean, you can walk through these and see the equations. I'm pretty sure all these equations I've double checked them. But I mean, you can see how they did this in 2 pages here with minimal number of equations. So I tried to walk through and at least show you this same information. One thing you'll learn in dynamics too is I omitted these forces. You see these forces acting on the centroid? There's a X and Y force. I just omitted those. Technically, a free body diagram requires these as well, because this thing's not just balanced. It could be spinning but moving in space. And we'll do this in dynamics when we get there. But for now, just recognize that those are balanced forces as well. All right, that's all I have. Any questions about or comments about anything? All right, I will see all of you on Monday, Monday. Have a good weekend, everyone.
You too.
Don't get cold. Not too cold.